Greetings to all my tech heads out there in the KevTechify Nation. And if you're new here, welcome. In this episode, we're going to look at wide area network operations. We'll be discussing WAN standards, WANs in the OSI model, common WAN technologies, WAN devices, serial communication, switch circuit communication, packet switch communications, and then finally we'll look at SDH, SONET, and DWDM. This episode is part of my series on enterprise networking, security, and automation. I'm Kevin here at KevTechify. Let's get this adventure started. As we talk about your wide area networks and the technologies they're using, we also need to think about what protocols, what standards are being out there. Now, there's about 3 organizations out there that deal with these standards. We have the TIA EIA, the Telecommunications Industry Association, and the Electronics Industries Association. The second one is the International Organizations for Standardization, and the third one is IEEE. TIA, EIA, and ISO sort of develop the overall concepts on what these standards should look like. IEEE, these are the engineers. We as IT professionals love the people who are in IEEE. They sit down and they make the standards from TIA and ISO work. They figure out the voltages, the light frequencies, how far stuff will go, what the sizes of the connectors are. And we as IT professionals, some of us may look into IEEE and see what it is, but for most of us IT professionals, we just take what IEEE says. Okay, this is your Ethernet standard. This is your standard for wiring up an RJ45. Now, this standard includes how wide that RJ45 is, how tall, where the pins are, where they're located, how big the contact area, where the clip is, what the physical description of those clips are. It describes all of that. Us as IT people, we just say, okay, here, thank you for the standard. We're going to use it. And so these organizations, these all work together to figure out the standards we're using with our wide area network connections. We also need to see how these different standards and where the WAN concepts figure into our OSI model. And our OSI model is the 7-layer model that describes how computers move across networks from the device to device. We're concerned with the bottom 2 layers. The physical layer down here describes the electrical, mechanical, and operational components to transmit the bits. So signal strengths, the actual voltage and amperage of the electricity, the wavelengths of the light that are being used in fiber. It describes all that. And there's three technologies that are typically for WAN connections at the layer 1, the physical layer. First one here is the synchronous digital hierarchy, the SDH. Second one is SONET, which is the synchronous optical networking, and that has to do with fiber, so that is SONET. And then the third one that usually down here is this dense wave division multiplexing. So dense wave division multiplexing. And what that is actually using different types of light or different frequencies of light, different colors of light across one fiber optic connection to get multiple connections to go across. At layer 2, this is where we start looking at how this data is going to be encapsulated into a frame. Now, for broadband, this is where we're looking at stuff like our cable and DSL connections. So how are those configured? How are those setting up? We also look at wireless technologies, and there's a whole bunch of these technologies here what we're looking at. We have something called Metro Ethernet. This is a high-speed WAN connection. We have multiple protocol label switching, MPLS. That's the ability to get multiple connections, multiple point-to-point connections over a single connection. Then we also have our point-to-point connections. That's all described here on our layer 2 for WANs. We have HDLC. HDLC is our high-level data link control, which is, it's not as used as much as it used to be, but it's still out there and you may run across it. We have frame relay. Frame relay used to be the gold standard on sending data over a WAN connection, but that has been replaced with other technologies like Metro Ethernet and MPLS. And then we have ATM, asynchronous transfer mode. That's another legacy technology. Hopefully you're not going to run into it, but you may still. And so what we see here is there's a bunch of different standards that have to work together to get our data across these wide area network connections. As we look at our wide area networks, there's some terminology that we need to cover. We're going to cover the common ones. We're going to cover about 10 terms here, but there's also a bunch of other little ones depending upon the technology you're using. But for the most part, here are some of the common ones. First one here is DTE, or the Data Terminal Equipment. What the DTE is it connects that subscriber LAN, so your local area network, to the WAN communication device. And that could be like a modem. And so this may be a modem at this point. So your router here, and so this is the company's router to the modem. And so the DTE connects into that modem. Then we have the DCE. The DCE is data communications equipment, and this is used to communicate with the provider. And so this takes the signal that the provider gives you. The signal, the provider could be giving you a cable connection, a DSL, a fiber connection, a T1 connection. It takes that signal and turns it into a signal you can use on your network. So it turns it into a copper Ethernet cable. It turns it into fiber Ethernet that you can use on your network that will connect into your DTE, into your router, into your network. So we have the DTE, DCE. Now, some of you may be familiar with the DTE and especially the DCE end of a serial connection when you configure the routers. Remember, on the DCE end, that's where you set the clock rate. And so a lot of people remember DCE, that's where we set the clock rate. And if you think about it, this modem, who controls this modem? Who controls that speed? Your internet service provider. So at home, for your internet connection, you have a cable internet connection and you get 100 meg download from your cable provider, right? And that's what what determines that speed? How much you're willing to pay, right? And then based upon how much you pay, your internet service provider sets that speed. Well, if that internet provider would say, okay, you pay this much to get 100 megs download, and they said, okay, and then they sent you an email with instructions on how to set your speed, and you could set that speed anywhere from 10 megs up to 1,000 megs per second, but you're only paying for 100 meg download. I got a feeling some people would set it a little bit higher than just that 100 that they're paying for. They would set it up to the maximum speed, get the maximum bandwidth. And that's why providers tell you what clock rate you're going to connect at, because of what you paid. Because if you got to set your clock rate, you're going to set it as high as possible. And so that's where we set the clock rate on the DCE end. Then next question, or next term we have here is what we call the CPE, or the customer premise equipment. And what that is it's this yellow square here. This yellow square represents all the equipment, the DCE and DTE equipment located in your company, sort of on the edge of your company. And so mainly it's the DCE and DTE that represent this customer premise equipment. Then we have two more terms coming up. Right now we have the demarcation point, or point of demarcation, depending upon how you do it, point of demarcation, and then another one called the POP, or point of presence. Most of the time, the POP, the point of presence, and the demarcation point are the same places. They're the same places. And the point of presence is the point where the subscriber connects into the service provider network. And so what we're doing here is this modem is going to connect into the service provider network right here on this edge. The point of presence, the demarcation point is that physical location. It's in a building or outside your building that officially separates the company's responsibility and your service provider's responsibility. Here we have enterprise edge, service edge. And so for enterprise edge, the company is responsible for everything going after the point of demarcation, which is here. Service provider is responsible for everything here. Now, that point of demarcation is typically a physical little plug on a phone box, on a cable box, on a service box, where the service provider provides that connectivity up into that point, and then you are after that. And what happens is when you call up and say, hey, service provider, I have a problem with your connectivity, they're going to walk you through a couple things, but they may eventually send out a tech. First thing that tech is going to do is disconnect that cable, plug it into one of his testers, and if it tests good, he's going to say, I'm sorry, up to here, that connection is good. After this connection, there's something wrong. And that something wrong is your responsibility. Now, if that tester comes back and says, oh, yep, there definitely is a problem between this point and the central office, then the service provider is going to fix it. But that's sort of that point of demarcation where that responsibility of the ISP ends and your responsibility starts. And so, like I said, the POP and that point of demarcation, those are usually the same thing. Minor differences here. Basically, that point of presence, that POP, is more of a logical boundary. So when you draw a logical diagram, that's what it is. That point of demarcation is that physical connection from the service provider into your network. It's that where you can go and physically touch that connection. In theory, they're both identical. One is logical, that's POP. The point of demarcation, that's a physical connection. The next term here is what we call the local loop. Some people call this the last mile. And what this is the connection between the central office, your ISP, and your customer premise equipment. The connection between your ISP and your company. It's the physical connection. Most of the time, it's either a copper connection or an Ethernet connection. Some of the newer technologies even make it a wireless connectivity. But it's that point, it's that connection that goes from your company to your ISP. And so that's that local loop or the last mile connectivity. This local loop or last mile is usually the responsibility of your service provider, but sometimes it's not. And so make sure when you're looking for your service provider, you understand whose responsibility that local loop is. Then this local loop connects into this central office. This central office is the provider facility, or it could be a building that connects the customer premise equipment to the provider network. So the customer premise equipment, your company, goes through the local loop, that last mile, and connects into the central office. That's where they connect you into their network. Once we're inside of their network, then we look at, well, how does their network work? And there's a couple different ways to doing that. One is we have what we call the toll network. And that toll network includes backhaul, long haul, all digital fiber optic communication lines, switches and routers, and other devices inside your service provider network. And so this is your service provider network. And what we're looking at is this toll network, everything that happens up here in the cloud. And once again, if you are this company over here and you're looking to get internet provider, you're not necessarily going to be concerned with exactly what's happening in the cloud here, just as long as you get your connection and your connection meets your service level agreement. In here, in this whole network, we could have the backhaul network. Then that connects multiple access nodes of the service provider, where we have those interconnections. We could also have a backbone network where it's large, high capacity networks used to interconnect different service providers and networks to create a redundant network. And we have all of this working together to give you your internet network connectivity, your connectivity to remote offices, to keep your company up and running so they can continue to make money. If you like this episode on wide area network operations and you get value out of it, and depending upon what platform you're using, please click that like button, give a 5-star rating, subscribe to my channel, leave a comment. Doing this supports the channel, which in turn helps me bring you more great content. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. As we look at our WAN connections, there's a handful of different devices we can use on our WAN to make the connections actually happening. We have our DTE devices. That's usually in your company. These routers are your data terminal equipment that they connect into DCEs, and the DCEs here, your data communications equipment, those are the devices that sit between your service provider and your company. Now these DCEs, they could be several different things. We could have a voice band modem here. This, I'm really hoping your companies don't use this anymore. This is old. This is those old dial-up modems. I do know that there are used in a couple places around now, especially in like a remote office where you have like maybe the auxiliary port configured into your routers or something like that. But to use normal business across the dial-up modem in today's world just typically does not work, but they are still out there. Then we have DSL and cable modems. Now, these are typically known as broadband modems. Broadband meaning a higher speed network. And they're digital. They connect to your data terminal equipment. They change this DSL signal, this digital subscriber line, this digital signal, once again, into a signal you can use on your company. Copper Ethernet, fiber Ethernet. And they're provided by your provider. They have that connection into their networks. And so we have the DSL modem and the cable modem. Then we have what we call a CSU DSU. What these are different, or two types of connections. They have to work in a pair, and it connects a digital device to a digital line. Digital line like a T1 would be an example here of that. And this, once again, is set up and controlled by your provider, your service provider, that gives you that connection to them so they can control that. They control the speed and the connectivity, your IP addresses, and then they provide you a port that connects here back into your routers, onto your network, your DTE, your terminal, your data terminal equipment. You could have an optical converter. This takes fiber in and once again changes it to a signal you can use. Different types of fiber, but they all have to convert that light signal into a signal you can use on your network. And then we also have our wireless access points, a wireless router. And it could be that $100 router you got from a big box store, buy it online, or it could be a leased frequency you're using, and that would be leased from like the FCC, where you're permitted to use that, and it's a much more complicated, much more expensive, but you get a lot higher bandwidth through there. Now, to connect all these up, we have our WAN core. This WAN core has layer 3 switches, it has routers in it, It gives you multiple high-speed connections through your network. This is typically, once again, your provider at this point. And as long as you have your connection in on one side, connection out on the other side, you're not necessarily concerned with what's happening in here. Now, if you're the provider, the other is true. You're concerned with what happens in this cloud, but you're not necessarily concerned what happens after it leaves the DCE end here. And so if you're the provider, you're concerned with what happened in the cloud. How do we get our data going across there? How do we make sure the data gets to the right DCE equipment? But once it gets to the DCE equipment, they plug their device into your DCE, and you don't care what they do on the inside of your company. And so it depends upon what point of view you have to concern yourself with how these connections all work. But DCE here converts it from one signal to another signal. Typically think of that as modems. And you convert it in from your provider signal into a signal you can use onto your network. And then the data terminal equipment that connects it into your network. Almost all network communications occur using a serial delivery mechanism. Serial sends that data, it transmits bits sequentially over a single channel. And what happens here is over the signal channel, one bit goes across and another bit goes across and another bit. So one has to follow the other. It's a long line of bits going across there. If we use parallel communication, we can send multiple bits across there at the same time, all on these data channels. Up here, serial, we only have one path across. Down here, we have 8 paths across to send data. So it happens 8 times as fast. But as the cable length increases, the synchronization time between those multiple channels becomes more sensitive to the distance. So the longer you go, the harder you're going to have to control the sending of the data across that parallel signal. And then because of that, parallel communications are typically used in shorter distances, where serial communications, they can run over longer distances. There are 2 methods which we can actually get that data physically across the network. One is the circuit switched method, and the other one is the packet switched. The circuit switched method is definitely the older technology. Think about this like making a phone call. And what we have to picture here is a traditional phone call, like the ones that your parents or maybe even your grandparents had, where they got the telephone from the telephone company, and it's not a voice over IP line, but it's a normal telephone. What it was is when you made that phone call, and so phone A is going to call phone B here in our conversation. And when you made that phone call, it came up with the best path through the network. And that best path through the network may not be the most direct based upon congestion and what's up and down. But once it establishes that path through the network, it continues to use that path for the entire phone conversation. So as long as you keep that phone up, as long as you continue to talk to grandma, that phone conversation will travel that exact same path through the network. It will never change until you hang up. And then when you call grandma again, it may take a different path, but as long as that communication stays open, as long as you don't hang it up, that path will stay there. And so we have a complete circuit through the network, and it stays for that entire conversation. Now, how this goes with computers is this circuit switched, or we can call it even a channel switch, happens between 2 points. It establishes a dedicated virtual connection through your service provider network before communication can start. And so before it starts, it has this communication circuit. It uses that circuit. All communications goes over that circuit. And now the 2 most common types here are what we call the PSTN, the public switch telephone network. That's the old school phone network where you call up your phone company and say, hey, I want that phone line. Once again, it's probably your parents, it's probably your grandparents that had this phone system from the old telephone company. It's not voice over IP, it's not cellular technologies, it's the old school phones here. The other one here is ISDN. ISDN, the Integrated Services Digital Network. And what that was is it used the same wires and a lot of times the same switching in the central offices of the phone company. It used the same wires, but it had a dedicated circuit through the network for the duration of the communication session. Now, this ISDN, we would send communications across there. And with the PSTN, you could get internet over it, but that was a maximum of 56K per second. 56K per second. Well, not megabytes, but K per second, kilobytes. And so public switch telephone network, that was 56K. When we take that from an analog signal, which the PSTN was, changed it into a digital network, you could get speeds up to like 300K per second. And so comparing those two, that was really fast. But looking at today's standards, that's not really fast. That's why a lot of these circuit switch systems have went out. Plus, these circuit switch systems weren't very efficient because one communication channel used it, even if there was a pause, like right now, and you paused and grandma thought of her answer and gave it back to you, you weren't sending any data across it, but you still had that circuit dedicated to you. So it was not very efficient. The newer standards, packet switch, is much more efficient. Occasionally you may run across the circuit switch network nowadays, but for the most part, these are legacy. You shouldn't run across these very much. In a packet switch network, we are not looking at the entire conversation, but the packets. Remember, in the OSI model, we get packets of information. That big piece of information broke down into smaller packets. Then that packet can be transported across the internet. Packet switch works by routing each packet individually across the network. Each packet could take a different path across the network. So we have the big message, and this is, you think about this is internet communication. Any communication over the internet, we break down, take your big message, break it down into smaller packets, and then each one of those packets can travel a different path. And so from server 1 to server 2, let's say you're syncing some files, and each of those files gets broken down into thousands of different packets. The first packet sent out here, packet 1, it could go up here, it could go travel across our network, take the most direct route, and get to server 2. And so this could be packet 1, right? But because of congestion, and let's say on this device right here, we have a queue, and the queue is starting to get full of traffic. The routing protocol, depending upon which one you could use, could notice this. And instead of routing the next packet, packet 2, through this device that's being congested because of the queue, we could route it up and around. And it could come down here. And so packet 2 could travel a different route. Well, packet 2 is traveling here, a backhoe comes here and cuts this line. And now all of a sudden, packet 3 has to travel down here and take this route. And it gets to the destination. And all these packets travel through the network. They travel through, they get to their destination because of how the packets are set up. They have sequence numbers. They can be reassembled in the correct order. The message gets through there. Now, packet switched is much more efficient because if there's a lull in the conversation, we don't send anything, but other devices, other users could be sending information at the same time using those same connections, using those same routers and devices going across the network, going across the internet to get there. Now, there's some common technologies here that we see. First one we have is Ethernet WAN, also known here as Metro Ethernet. That's one of these packet switch technologies we see in a WAN environment nowadays. Another one is MPLS, multiple protocol label switching. We see frame relay, but like we said earlier, this is more legacy. Hopefully don't run into this. And we see ATM, asynchronous transfer mode. These here hopefully are legacy and you don't run into them. If you do, I would look at replacing them with either MPLS or Ethernet. But these are all packet switch. Each packet has the potential to take a different path. And notice I said potential. If when that second packet gets there and the routing protocol determines that the path that the first packet took is still the best one, it's going to send that. And most of the time it will. Because to send all those packets, a lot of times, usually takes less than a couple seconds. And usually your networks don't change that quickly. But if they do, the networks could respond. The routing protocols could respond quick enough and make a change to how that packet gets through the network. As we talk about WAN and the technologies used, we need to spend a little time talking about fiber. Fiber is by far the best technology, the best medium to use over our wide area network connections. Fiber offers a lot higher speed than traditional copper. They offer longer distances, where copper is usually good for a good mile to 2 miles to 3 miles before you need a repeater. Some types of fiber optics, they can go up to 30, 40, 50. Some are even up to 100 miles before they need to have a repeater put in. And so we can send that data for a long ways before we need to go in, recondition it, and retransfer it out again. When we look here at the OSI model, there's two standards for fiber. One is the synchronous digital hierarchy, SDH, and the other one is synchronous optical network, or a SONET network. These are pretty common in today's network. SDH is a global standard for transporting data over a fiber optic. SONET is the North American standard that provides the same services as SDH. Basically, SONET is North America, SDH is the rest of the world. And so they're almost identical in a lot of aspects. SDH and SONET, they look at how we can send multiple communications of data, voice, and video using lasers over long distance. Lasers are light emitting diodes. How can we actually do that? That's what SDH and SONET does. There's a new kid on the block, DWDM, or dense wave division and multiplexing. It's a newer technology, and what it does is it increases the carrying capacity by using multiple wavelengths of light, different colors of light. And what happens is there's different electrodes or different LEDs that produce different colors of light, different shades of light, where there's a sensor on the other end of the cable that can detect those different colors of light, and they can separate out. So that way you can send one stream of data using one frequency of light. You can send a second stream using a second light, getting twice as much, 3 times as much, 4 times as much data across that connection. Now, it's a little bit less distance than if you were to use the SDH SONET methods of just sending a single light source across, but we're still looking at 20, 30 miles of using this dense wave division multiplexing. It was my pleasure to provide you with this wonderful episode on wide area network operations. If you liked this episode and got value out of it, and depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All my socials and contact information are on my website, KevTechify.com. You can get all these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation. In the bottom right is one of my favorite videos that I linked just for you. Thank you so much for watching this episode of my series on enterprise networking, security, and automation. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.